Lucas, is that his name?
Yeah.
Father, thank you for today and for our time together to study these things of chemistry. Father, we pray for Lucas and for the impending knee, whether it's surgeries or whatever he needs to have there. Father, just pray that you give him peace in his heart. Lord, show yourself to him. We know that he doesn't believe that you are, that you exist. Father, would you be kind to him in his need and even in hard-heartedness. Lord, we pray that you would just do wonderful and kind and wondrous things in the lives of our students for the rest of this semester. We ask this in Jesus' name. Amen. All right, my friend, we are a little more minutia. When I say that, we might have another problem first, which should be good. Let's do one. Okay. So this is going to be example 11.2. And this is still following up on this formula that we put into play. We have Cg equals Kpg, where Cg is our solubility. That should be capital P. K is a constant that varies with temperature, and P is our pressure. This is called Henry's Law. We're going to look at it a slightly different way this time. A certain species of freshwater trout requires a dissolved oxygen concentration of at least 7.5 milligrams per liter. So it needs 7.5 milligrams of O2 per liter. Could these fish thrive in a thermally polluted mountain stream where the temperature is at 30 degrees centigrade? Okay. Partial pressure of atmosphere of atmospheric oxygen at this temperature. Water temperature is 30 degrees. Partial pressure of atmospheric oxygen is 0.17 atmosphere. Use the data from figure 11.8 to estimate the value for Henry's law constant at this temperature. Okay. So this has to do with altitude, not the temperature, but the way they word the questions. So for this one, we're given a chart that we looked at before. I'm literally going to hand it to you because I know you're not looking at this. And what we want to know is what this is going to tell us K. Okay, so what is K at 30 degrees for oxygen?
So 1.2.
Yeah, 1.1.
I would say like 0.1.
What if we went 1.2? So our K is, we know that Cg equals Kpg, right? And so this is going to be 1.2. Our pressure here is going to be 0.77 atmospheres. To solve this problem, we're going to solve for C, right? But then this C is not going to be in the units that we want because we need to get to 7.5 milligrams of oxygen, so we're going to convert from there. Okay? So, begin to set up our problem, right? And so the unit here is, you need that. It's moles per liter at 1 atmosphere. ahead and work this out, and what we get is Cg equals 1.2 moles per liter atmosphere times 0.77 atmospheres. That's going to cancel out, and that's going to leave me with moles per liter. But the units I need are milligrams per liter, right? So I've got to get from moles to milligrams, right? So to do that, I'm going to put 1 mole as my denominator, and I need the molar mass of oxygen.
Just oxygen or O2?
Oxygen gas.
Okay, so
Sorry.
the 32.
Right. So 32 grams per mole. But then, this is in milligrams, and this is in grams, so I've got to go ahead and I've got to put 1 gram as my denominator, and I've got to put 1,000 milligrams as my numerator, right? So when I solve this, what do I get?
I got 67,968. Double check.
Yeah, double check.
Yeah, that was 29.568. 29,568.
Let's. Here's our problem. This is 1.2 times 10 to the negative third. Moles.
That changes.
That'll change it quite a bit more. So we have 0.0012 times 0.77 times 32 times 1,000. That just became a completely crazy number. That was the right answer. What do you got?
29.568.
Oh,
No. Oh, okay. No. That's actually right.
so if we just go 0.0012, remember my calculator does not do well with this, times 0.77 times 32 times 1,000, should get about 6.5.
I don't know what, so I'll try again. I'm still getting the same.
Really?
Yeah.
0.0012 times 0.77 times 32 times 1,000. And that did not come out right. Well, now I know I'm doing it right. I did this problem earlier. I have the same answer they have.
I think we're forgetting
Oh, brother.
okay, to the negative.
Let's do it one more time.
6.5.
This will explain why I got the right answer. because I was just going off of the numbers I had on my page, not off of what I had up here.
Okay.
Then when I went up here, it got a crazy answer. One more time. 0.0012 times, 0.0012 times 0.17 times 32 times 1,000 is 6.5. Okay. All right. Well, let's do the next one. Quick reminder, as far as the test, you will take it the 14th online. It's going to run through from the 10th to the 14th. That opens, what, Thursday, I guess? So we'll be going Thursday through Monday on that test. Okay. Follow-up problem. Oh, and so the answer, what was our answer there? It was 6.5. So the question was, we did all that math to answer a question. At that temperature, is there enough oxygen for those fish that need that to survive? And the answer is no. Okay, follow-up question here. What dissolved oxygen concentration is expected for a stream when it returns to a normal summertime temperature of 15 degrees centigrade? So, you look at it at 15 degrees centigrade, and you're right there, right about in the middle, so you get about 1.5. Right, so this is 1.5, what is this, moles per liter atmosphere, okay? So we have the same formula. We have C equals Kp, right? I've got my K here. I just need to multiply it by my pressure. My pressure is the same. My altitude did not change, right? So this times 0.77, that's a 1. What?
1.7.
Oh my goodness. That's where my problems went. My own bad handwriting. 0.17 atmospheres. Now, I again have to convert from moles to grams, so I'm going to multiply that by my molar mass. 1 mole of molecular oxygen is going to be 32 grams per mole, and I need it to get into kilograms, so
Times 1 to
I've got to put 1,000, is it kilograms?
It's milligrams.
Milligrams, I'm sorry, thank you. We have something coming up with kilograms in a minute. So I have 1,000 milligrams per gram. That gets real easy when it's just all written up there, right? So 1.5 times 0.17 times 32 times 1,000, and you get 8.2 milligrams per liter. Okay, there we go. So now we turn the page. It's going to give us some information without having us do any problems with it for just a little bit. Deviations from Henry's law are observed when a chemical reaction takes place between the gaseous solute and the solvent. For example, the solubility of ammonia in water increases more rapidly with increasing pressure than predicted by the law. So Henry's law, right, C equals Kp, tells me that if I increase pressure, my concentration should increase proportionally, right? I've got a proportionality constant here. This is not always true. There are some times when I'm dissolving a gas into a liquid to form a solution, that the concentration outpaces the pressure. For example, when I do ammonia here, so NH3. When I do NH3, this does not follow a linear constant here. As I increase my pressure, this actually increases a whole lot more. It's a whole lot more readily dissolved. And so you've got to ask yourself, why? The reason is because I have intermolecular forces at work here that are stronger than anticipated. When I take NH3 and I add it to oxygen, it's not just dissolving in this, it's actually often, to a certain degree, reacting with it. And so I will get NH4 plus hydroxide. Right? So it's forming a base. It's more soluble than expected because of what it's doing actually even to the solvent. Gases, this is another factor here, or another observation. Gases can form supersaturated solutions. So we know that because we talked about the carbon dioxide. If a solution of gas in a liquid is prepared either at low temperature or under pressure, or both, then as the solution warms or as the gas pressure is reduced, the solution may become supersaturated. So this is just anecdotal stuff, but it's kind of wild. So what's the name of this lake? Lake Nyos is like a mountain lake in Cameroon. And there's a village over here. I've been drawing a lot today. And 1,700 people died. And I know it's good stuff. In 1986. And they believe because of carbon dioxide poisoning. This is a volcanic situation. It's fusing CO2 gas into here. Down here, saturated, right? It's cooler. We know about cooling curve, or about absorption, partial pressures, that the cooler it is, the more it absorbs, right? So this is going to be this is my temperature, right? This is going to be my partial pressure. It's more readily is absorbed in it, the cooler it is. So I literally can hold a whole lot more CO2 down here. What they think happened was that there was some overturning or some upwelling, and all of a sudden this CO2-rich water came up to the surface, heated rapidly. It's not nearly so soluble at this temperature, and so it followed its pressure gradient. And then, if you've ever seen this with carbon dioxide, you can do like vinegar and you can have a candle laying there, and you can do vinegar and baking soda, and in a tall cylinder, and it'll fill with carbon dioxide. It'll push out the other gases. Well, that carbon dioxide is more dense than the air around it, and you can literally pour the carbon dioxide onto that match and extinguish it. And which is just crazy cool. And so they think that's literally what happened here. It's odorless, it's colorless. These people never saw it coming, and they asphyxiated and died. So why that's all in here, I don't really know. But they wanted you to know that, so now you know. Plus, you know, a cool trick to do with kids. My kids have to do something for a science fair coming up. Maybe we'll do that. My wife hasn't told me what the boundaries are yet, though. My buddy did an electromagnet for his kids, so now that's out. I can't do that. He only has one. I have 3 that are in this thing. Yeah. All right. Solutions of liquids in liquids. So we know some liquids are not, they don't mix well at all. Oil and water, that doesn't mean they mix none. Right? But mixing has everything to do with intermolecular forces. So if it has a lot of van der Waals forces, and the other liquid has a lot of van der Waals forces, those two things mix very well. We have a principle for that. Thing we say in English, you have to tell me if you say it in Portuguese or not. Like dissolves like. Have you ever heard that? Or like likes like?
Mm-hmm.
Yeah, okay, so like, likes, like. So polar, polar, non-polar and non-polar. I can't get water and oil to mix very much. I can't get water and gasoline to mix very much, but I can get oil and gasoline to mix really well because they're going to have van der Waals forces between them. Similarly, I couldn't get ammonia to mix with gasoline. I can't get water to mix with gasoline, but I can get water and ammonia to mix very well because they both have these strong dipole moments. So, a definition of this mixability of liquids is miscibility. Is it miscible? I'm probably going to misspell miscible, even though I've been reading this word since I was in 7th grade. Hey, I did pretty good. All right, miscible. Infinite mutual solubility. In our own way, we were talking about this the other day. If I have two liquids and I'm pouring one into the other, well, one's the solute, one's the solvent. But what if I pour more of the other than that one? Because they're mutually soluble. Okay. Mm-hmm. So this is the idea of miscible or miscibility. Of course, then there's the idea of two things being immiscible, which doesn't mean there's no solubility, but it's extremely low. So if I have two liquids and they are fully miscible, let's say they're different colors. I've got a red and a blue. Then when I add the two together, the resulting mixture is going to have no demarcation whatsoever. I'm just going to have one purple liquid, right? Mm-hmm. If I have two that are not miscible, right, immiscible, then I'm going to end up with a layer here. I'm going to have red, and I'm going to have blue, and maybe if you wink at this just right, you'll see a little hint of purple. If I had two that have partial miscibility, then I'm going to have a faintly blue-red on top, and I'm going to have a faintly red-blue on bottom, because just a little bit of this red will dissolve in here, and just a little bit of this blue will dissolve up here. So they'll change color slightly, right? But they're not going to just readily mix. We're not going purple with this thing. Okay. All right. Solutions of solids in liquids. Let me erase all this, and we'll go on to the next thing real quick. The dependence of solubility on temperature for a number of solids in water is shown in solubility curves. Reviewing such data indicates a general trend of increasing solubility with temperature. So here's the thing. When I have a gas in a liquid, my solubility as temperature increases, my solubility decreases, right? For a gas. It's the opposite for almost all solids, though. Okay. And this is how we get supersaturated solutions of things like sugar, right? And of course, by lowering the temperature, I can get a supersaturated solution of carbon dioxide in water. Temperature dependence of solubility can be exploited to prepare supersaturated solutions of certain compounds. A solution may be saturated with a compound at an elevated temperature and subsequently cooled to a lower temperature without precipitating the solute. The resultant solution contains solute at a concentration greater than its equilibrium solubility at the lower temperature, and it is relatively stable. Precipitation of the excess solute can be initiated by adding a seed crystal, we talked about that, or mechanically agitating the solution. Okay, great. Let's talk about colligative properties. You heard this term before? Or remember it?
I remember it.
All right. Colligative properties. Colligative properties are properties that depend only upon the total concentration of the solute, not the identity of the solute. As soon as you get that, I'm going to give you a little bit of a caveat, though. This is not my favorite definition of this. I think it's a little misleading, frankly. So they're going to give you some examples of colligative properties. Examples of colligative properties include lowering of vapor pressure, increasing the boiling point, decreasing the freezing point, and osmotic pressure. Let me give you a couple graphs here. Let's deal with boiling point elevation, okay? Okay. So, what we have here is, this is going to be my solute. This is going to be my boiling point, okay? Regular water boils at 100 degrees, right? So if I have 0 solutes, it's going to boil at 100 degrees centigrade, right? What this is saying is its boiling point elevation. So as I add more solute, my boiling point is going to go up. I would have to add more energy to get it to boil, okay? It's saying boiling point is a colligative property. It only depends on the concentration, not the type. So if I added, we're going to just be hypothetical here. Let's say I wanted to raise my boiling point and this did it by 5 degrees here, okay? 5 degrees centigrade. Again, I'm just making up numbers. And this was with, by adding 100 grams. No, we better not do grams, we better do moles. That is going to matter. Let's do 1 mole, okay? It's saying that I can raise that boiling point, the minimum temperature required to make it boil, by 5 degrees, whether I add 1 mole of ethanol, or 1 mole of sugar, or 1 mole of iron, or 1 mole of anything, okay? Because it depends only on the concentration, not the identity. That's true, kind of. If I added 1 mole of NaCl, I did not add 1 mole of NaCl. What I added was 1 mole of NaCl, or 1 mole of sodium, and 1 mole of Cl, because this is ionic. It's going to ionize. It's going to dissociate. Effectually, I'm adding 2 moles of solute, not 1. So this, the way they're defining not the identity, is really misleading. If something ionizes into 2 parts, I'm adding 2 moles. If it ionizes into 3 parts, I'm adding 3 moles, right? So I would need half as many moles of sodium chloride as I would table sugar to get the same result. So, not my favorite definition. I don't think we're going to get to how that plays in today. I assume we will next time. I haven't looked that far ahead. But just bear that in mind and we'll do some problems and stuff with this, okay? All right. Are you familiar with the fact, you know, like if you're boiling pasta and, you know, if your water's boiling and I add some salt to it, it stops boiling, right? Temperature will raise, it will resume boiling again. That will cook my pasta actually faster, which sometimes is advantageous, right? Another thing is freezing point depression, right? So it'll freeze at 0 degrees. If I add a bunch of solutes, it's got to deal with the solutes before it actually forms ice, and so that'll lower the point at which it freezes. It affects osmotic pressure, affects vapor pressure. If I add a bunch of solutes to it, the solvent is going to adhere to those solutes, and so they're less free to go up as vapor, and so it lowers the vapor pressure around it. So again, the idea is it doesn't, I really just wish this said total concentration of solutes. That, I think that would probably help because of the ionization factor. Now, that said, here we go. Several units commonly used to express the concentration of solute components were introduced earlier. For example, molarity, right? So we did molarity. That's the one we've been working with almost exclusively. That's moles per liter, right? But there are other concentration units and we need them here. And we'll see why in a second. Another one is mole fraction. So mole fraction is it's if I have moles of A divided by moles of A plus moles of B, right? So if this is my solute, I want the number of moles of solute divided by the moles of solute plus solvent. That'll give me my mole fraction. By the way, if I once I get my mole fraction, I already know the other one, right? Because it's out of 1.
Mhm.
It's basically a percentage. The other one that we're going to deal with is molality. Molality equals moles per kilogram of solvent. So we're going to be dealing with these two coming up. And of course your question should be like, why? Right? This is moles of solute over liters of solvent. Okay? But this is a density situation. 1 liter, that's a volume thing, right?
Mhm.
But how much is in a liter depends upon my pressure and my temperature. My moles of solute wouldn't change, but I could have moles of solute in 1 liter at standard temperature and pressure. But if I reduce the pressure, if I increase the temperature, I don't have a liter anymore. I might have like 1.1 liters. And so that's going to change my molarity. And so that's going to make it difficult to deal with colligative properties and calculations. Whereas, if I do a mole fraction, I don't need to be worried about the volume of this changing based on pressure or density. I can calculate the moles of each one. If I have a certain solvent, its mass is the same regardless of the atmospheric pressure of the temperature. And so moles of solute divided by kilograms of solvent is going to be consistent. It's going to be helpful. So that's the reason that we would go ahead and do this. I think we're ready to go. Okay. So, the antifreeze in most automobile radiators is a mixture of equal volumes of ethylene glycol and water, with minor amounts of other additives to prevent corrosion. We want to find both the mole fraction and the molarity. Okay, so we're going to find mole fraction and molarity of ethylene glycol. This is C2H4 OH2 in a solution prepared from, we have a 2.22 times 10 to the third grams of ethylene glycol, and 2.00 times 10 to the third grams of H2O. Given the travesty I did earlier, let me make sure all these numbers are right. 2.22 times 10 to the third, 2.0 times 10 to the third. It's water. Ethylene glycol is C2H4. Okay. So we want to find a mole fraction first, right? So I need moles of ethylene glycol divided by moles of ethylene glycol plus moles of H2O. That'll give me the mole fraction for ethylene glycol. I could reverse this to do it for water, or I could just subtract it from 1, which is always my preference. So I want you to do that. I will be right back. All right, so to solve this, right, I need 2.22 times 10 to the third grams times molar mass, right? I need 1 mole. You know how much that is? That's what, 24 plus 4 is 28 plus 2 is 30 plus 32. What do you get on that?
I did 45, but I did it wrong.
Okay.
I just saw it was 2 OH, so I did 1 less O and 1 less H. So
Okay. Should be about 62, right? So 24, 28 plus 32 is
38 plus
30.
32 is 70.
Should be 60.
Oh,
28 plus 32 should be 60 plus 2, right? Should be 62, okay?
Okay.
And so that's going to put us at about 35.8 moles of this thing, right? So 35.8 moles for my first one. And down here, again, I'm going to include my 35.8, and I'm going to add the number of moles that I have of water. So for water, what do I have here? I have 2 times 10 to the third grams of water. And I go, okay, 1 mole of water is, what is it, 18 grams, right?
Yeah.
Okay, so I divide that by that, and that's going to give me 111 moles, okay? So if I divide 35.8 by 35.8 plus 111, run those numbers.
Yeah.
Okay, good. And now if I subtract 1 from 2 point, this is the mole fraction of ethylene glycol. If I want the mole fraction of water, I simply subtract that from 1, right? And that's going to give me what, like 0.756, is that right?
Yeah.
Okay, that'd be my mole fraction for water. Okay, well that's good. That's the first part. The second part is I need to find my, I said molarity. This needs to be molality. You just get so used to the same thing all the time. Molality. Okay. So molality is moles of solvent or solute divided by 1 kilogram of solute. So I'm going to write down these 2 mole fractions here. I've got 0.244 for ethylene glycol, and I have 0.756 for water. Okay? Now, I'm going to erase all this. I'm trying to find molality. Little m. Little m equals moles of solute over kilogram of solvent. Okay. I've got moles. So I'm going to work with this mole fraction. And I'm going to go, okay, I've got 0.244 moles of ethylene glycol over 0.756 moles of water. That's true, and this is the start to me getting my molality. From here, what do you see that I need to do?
Get the moles of water to go to kilograms.
Yeah. So to do that, moles, I've got to use my my molar mass, right? So multiply that by 1 mole of water is 18 grams, right? 18 grams per mole. And now I've got to get to kilograms. So I've got to do 1,000 grams per 1 kilogram. That will give me my answer. Yeah.
17.94.
Yeah, that's what I just got for those. That's correct. Very good. Forgot to turn it over to the back page. I'm like, how did they get that? And I got this. All right, very good. Well, let's do one more problem like this. What are the mole fraction and solubility of a solution that contains 0.850 grams of NH3 dissolved in 125 grams of H2O? Okay. So first thing we want to do is find our mole fraction, right? So I've got 0.850 grams times 14 plus 3 is 17 grams per mole. Okay, that'll give me moles of that. And I need that same number plus 125 grams times, I did that wrong. Gotta flip my sign. Okay. 1 mole is 17 grams. 1 mole is 17 grams times 18 grams per 1 mole of water, right? Simplify this, I've got 0.05. Is that right? That's right.
About 0.05.
Yeah, okay. Divided by 0.05, and this is moles, right? 0.05 moles plus 125 grams, yes it is. 6.944 repeating. You got that? We got 7.14 times 10 to the negative third moles of NH3. 3, that's the mole fraction for ammonia. Okay, good. Now I just need to take that and find my molality. Alright, so I've got 7.14 times 10 to the third moles of NH3. Right,
Oh, you need to make the water, need to take that out of one? It's to the
yeah,
negative.
to find the right. And so when I do that, I get 0.9928 moles of H2O.
Yeah.
All right. All right, so now I'm trying to find molality. That's going to be moles per kilogram. So I have 7.14 times 10 to the third moles of NH3 over 0.9928 moles of H2O times 18 grams per mole. Maybe 17.87, right? Something like that, in terms of grams, but I need to, of course, not have it in grams. I got to get to kilograms. So I got to keep going. I got to have 1,000 grams per 1 kilogram. This will give me my molality. Just got to do all the math on it. This is to the negative third, isn't it? I'll mess that up. So 0.00714 divided by 0.9928 divided by 18 times 1,000. Got it. That's good?
Mm-hmm.
Okay. Let's go on to the next type. All right. Calculate the mole fraction of solute and solvent in a 3.0 molars molal. This is molal of NaCl. Okay, so we're trying to find the mole fraction of both solute and solvent. So let's think about how to approach this, right? 3 molal tells me that I have 3 moles of NaCl for 1 kilogram of H2O, right? So I know my moles here. All I have to do first is do this, right? So I'm going to have 1 kilogram of water. I'm going to just automatically convert this to 1,000 grams times 1 mole over 18 grams. Now tell me the moles of water that I have here.
55.5.
5.5. Okay, so 55.5 moles of H2O. So now this isn't too hard at all. I've got 3 moles of NaCl over 3 moles of NaCl plus 55.5 moles of H2O. So 3 divided by 58.5. Seem right to you? All right, they like it. Life's good. Okay, let's do another one. This one steps up just a hair, which is good. The mole fraction of iodine, I2, dissolved in dichloromethane. So I2 in CH2Cl2 is 0.115. What is the molal concentration of iodine in this solution? So I know that moles of I2 over moles of I2 plus moles of CH2Cl2 equals 0.115, right? Is that right? Actually, I don't even need all that, do I? This is simpler than that. This is simpler than that. I can do it this way. Because what I want, these are fixed ratios, right? I know that for my other, that it's going to be 0.885 moles, right? So this is my ratio. I get for every 0.115 of this, I've got 0.885 of that, right? So I can go, okay, I've got 0.115 moles of I2 over 0.885 moles of CH2Cl2. I'm trying to get to moles per kilogram. This is already in moles, so I don't have to do anything with that. All I have to do is get back to kilograms. And this is easier than I was originally setting out to do, which is good. So all I need to do is multiply this by my molar mass of CH2Cl2. So give me that one. 55 grams per mole times 1 kilogram over 1,000 grams.
About 0.075.
0. That's not right. Let's make sure I have all my numbers.
Okay. I forgot one step. That's
Okay.
why.
Fair enough.
$1.53.
Yeah, about 1.5.
I did the bottom part, but I didn't do the upper part.
Okay. What time do we have? Do we have time for another?
46. Slightly.
All right. We'll do. Give it a shot. See if we got enough time. Start late.
Yeah.
Okay. You said I'll be there. I'm coming. I almost texted back to prove it. Okay. Intravenous infusion. This is a molarity and molality conversion. So going between the two. Intravenous infusion of a 0.556 molar aqueous solution of glucose with a density of 1.04 grams per milliliter is part of some post-operative surgery therapies. What is the molal concentration of glucose in this solution? So I have 0.556 moles per liter. What I need to find is the number of moles per kilogram. Okay? So if I have this many moles, I'm assuming 1 liter, right? I need to get the mass of a liter, and this is a liter of solution, right? Not just of water. So I need to figure out the mass of that liter. Right? So I've got 0.556 moles solute over 1 liter times, we better get into milliliters, right? So I got 1,000 mLs per 1 liter. Right. Now I gotta get to density, which is going to be 1.04 grams per milliliter. Okay.
And 2 kilos.
Huh?
And then 2 kilos.
Okay. Make sure I'm not skipping a step. I haven't solved this one yet. Liter times its density times 1,000 times 1,000 gives me my kilograms. Okay. Okay. Now this is going to give me